In this video, we'll try and have a go at this calculus prepping class task. So there's a variety of questions here that sort of cover most of the non-graphing stuff for this topic. So let's have a look. We can see in question 1 that Bill's got a piggy bank here with a balance of money in it. And we can see straight away that this relationship is not linear. So he's got time in weeks and he's got the amount of money that he's got in his account. Now we can see that in the first week it jumps $13. In the second week it jumps another $6. In the next week he loses money. He actually goes down $1. In the next one he's losing money again, and then in the final week he's gained another $5. So it's not a linear relationship, it's probably a cubic relationship. Let's have a look at what is happening. Question A is asking us, what's his average gain or loss between weeks 2 and weeks 5? So we're really just after average gradient this time. So what we'll do is we'll go for the gradient of this is just going to be y2 minus y1 over x2 minus x1. So if we give these some values so that we know what we're working with here, what we've got is, we'll call this one x1, y1, and we'll call this one x2, y2. So I'm really only interested in these values and these values, and they're going to go straight into our equation as we see them. So these average, if you like, rather than the gradient, is going to be 42 minus 41 all over 5 minus 2, and that is 1/3. We might answer this one as a worded answer, seeing as it's a worded question, so therefore his average gain during this period was positive 1/3 per week. All right, let's move on. So during which weekly interval was the gain or loss the greatest? Well, we can see quite clearly here in the first week that he had the greatest gain, and that was greater than any of his losses. So same deal, worded answer. In the first week, which was from T0 to T1, he gained $13, which was the greatest rate of increase throughout the period. Question 2, we're looking for some limits here. So this is just substitution really, the first example. So as the limit approaches 2, so all we do is we take this formula and we substitute 2 in. So as the limit approaches of x approaches 2 rather, we are looking for 2 squared minus 2 minus 3 all over 2 plus 2. Terrible writing, sorry about that. Let's fix that up. Nice and clear. Pop it in your calculator and it will be -1/4. So remember, that's the limit as x gets so close to 2 that it might as well be 2. Okay, and question B is not quite as simple as question A. If we went for as a straight substitution, it wouldn't work, because if you have a look at this, if I just go straight in like I did in question A, and I go in with a -4 squared plus 10 times plus 24 all over -4 plus 4, well, it doesn't really matter what the top simplifies to, because it's going to be something over 0, and that won't work because it's undefined. So this is not the way to do this question. Instead, what we're going to need to do is we're going to need to factorize it first, okay? So the correct way to do this is as the limit of x approaches minus 4. And then what we'll need to do up here is we'll actually need to factorize this. So we'll end up with x plus 6, x plus 4, all over x plus 4. And then these guys cancel one another conveniently. So what we end up with is a modified formula where we've got the limit as x approaches minus 4 of x plus 6. And this is much better because now we can go in with minus 4 plus 6. I shouldn't be lazy, should I? Hang on. As the limit as x approaches minus 4 will become minus 4 plus 6. And so the answer here is 2. So this is our final answer. Okay, moving on. In these ones, we need to find the derivative. Let's not use first principles, it's too slow. So we will use the formula. So remember, y equals ax to the n. So when y equals ax to the n, then the y on dx, the change in y over the change in x, is going to be n ax to the n minus 1. Right, let's solve these ones. So if y equals that, then the y to x is going to be 15x squared. Remember, so it's this one here times this one, and then this one minus 1. Same all the way across, so minus 14x minus 1. Any number here in front of an x just becomes the number. Really what's happening is the x becomes to the 0 and anything to the power of 0 is 1. Just don't bother writing it. Alrighty, moving on. This time we've got fx, so we're going to go the derivative function, or f dash x. Oh dear. 5 times 2 is 10, and 5 minus 1 is 4. And a minus 1 on the end there. Next one, g of x, so this is g dash of x. Just formalities. 1x becomes 1, and then 5 over 2 times 1 becomes 5 over 2x. And then we've got to take 1 away from 5 over 2 rather, so we end up with 3 over 2. So again, this little bit here, if you lost me there, okay, is just 5 halves minus 1. And remember that we'd better write 1 as 2 halves, so that became 3 halves. So that's back to fractions there. Alrighty, and in the next one, might be easy to get lost in a question like this. So what we might do is we just simplify this a little bit first. So this is equivalent to 5. So I'm not doing derivatives yet. I'm just still mucking around with the original equation here, just to make this nice and clear. And if I can simplify this, I'll do that as well. So I'll just simplify what I can. Can't do much with 5/8. They're just going to have to sit there. But 4 over 8, I can simplify to a half. So I'll do that just to make life a little easier for myself. And now I'll go through and I'll do the derivative function. So we're after dy over dx. And so that will become 15x squared over 8. It doesn't impact on the 8 at all, remember. And 5x to the 4 over 2. And that one is done. Next one, it's an fx. So we're going to do an... Oh, but before we do that, because we've got the x down the bottom, it might be easier to get that up on top. So I don't know if you guys remember this last year from index law, but what we can do is we can bring up that x and make it a -3 instead. So inverse, if you like. And so now we can do f dash of x just following our rule. So this will become -3x minus 4. And then let's just say that we were asked to give it in positive index form. That could also be written as f dash of x minus 3 over x on positive 4, just to get it back into positive index notation. And then the last one here, let's have a look at this one. Might start this one by doing a little bit of simplifying. So I'll do something similar to what I did over there in question D. And before we work out the derivative, and I'm jumping to an F here when it's a G, if we just keep it at the original function for a minute and we just break these into individual terms, this is going to be a bit clearer. All right, we can cancel some of this stuff. Let's do it. That can go down to a 2. That can go down to a 1. And we can't do much with that one on the end. So now let's see what we can do with this. We've got gx still. We're not going for the derivative yet. We've got x squared. We've got 4x. And I don't want x down the bottom, so I'm going to bring that up as a x to the -1 instead. That way we're going to be able to apply our rule. So now we can do the derivative function. So we'll have g dash x, that's going to be 2x, a 4, a -2x to the -2, because remember it's -1, -2. And let's just say, again, we were asked to do this in positive index form. We can do that. We've got 2x plus 4 minus 2 over x squared. Question 4, and we're still finding the derivatives, but this one's factorized. That's no good. So we're going to need to expand that before we can apply our rule. So let's do that. So we can also write this as y equals 3x squared minus 15x plus 2x minus 10. We'll collect any like terms. These guys are like, so let's collect them up. Now got y equals 3x squared minus 13x is minus 10. And now we're just after the derivative, so that's dy dx. Same rule as question 3, 6x minus 13, and this one's done. Next one, we're back into index notation again, so let's rewrite this so that we can use our rule. So normal function, not the derivative yet. We're going to go 7x, and then the square root of x can also be written as x to the half. And if we do that, then we're more easily able to use our rule. So let's do that. Let's jump into f dash x. That's going to give us 7 minus a half x to the minus 1/2. And I'm getting that from, remember here, that a half minus 1, or a half minus 2 halves, is going to be minus a half. And that one is answered, but it's a bit messy like that. So let's try writing it as f dash of x equals 7, oops, that 7 didn't really turn out, minus 1 over x, 2x to the half, Or another way of writing that would be 7 minus 1 over 2 square root of x. And we'll just write that in to be neat. Alrighty, gradient. So now what we're trying to do is we're trying to find the gradient of a function. Now when we have a look at this function, we can see that this one's a quadratic, so it's going to be a curve. It's going to look something like this. It goes through at +9, so that's a terrible drawing, but that doesn't matter. Now, what we're going to do in order to do this is use the derivative function. So we need dy dx, and that will be 2x minus 6. And then it's asking for that when x is minus 2. So now we just need to sub minus 2 in. So dy dx will be 2 times minus 2 minus 6, which equals minus 10. And so we could write this as a worded answer, and that might be something along the lines of y equals x squared minus 6x plus 9 has a gradient of minus 10 when x is minus 2. Okay, something new for us that we haven't talked about in class yet is the tangent to the curve. So what we might do is sort of draw what I mean by this. Okay, so if we have a Cartesian plane, we'll just move this stuff out of the way so it doesn't bother us when we're learning this. And we have a curve that looks something like this, for example. The tangent is, so what have we got? We've got a point minus 2, 18. Let's say this is our point here, minus 2, 18. The tangent is a line that's parallel to that point, okay? So that would be the tangent here. So in order to find that, what we're going to need to do is we're going to need to find a gradient at that point. And then what we'll need to do in a second step is determine the y-intercept or the constant so that we can write an equation for that line. So the first part of this is not new. We're going to find the derivative function f dash x is going to be 6x minus 1. And then we have got a x value here. So what we'll do is we'll substitute that in because we want to know what the gradient or the rate of change is at that exact point. So we'll go in and say, so that's great. That means that when x is minus 2, we've got 6 times minus 2 minus 1. So that obviously gives us minus 13. So we know that the tangent has a gradient of minus 13. So let's start writing. We remember that the tangent's going to be a linear equation, and we will remember that linear equations have the formula y equals mx plus c. So if you cast your minds right back to linear, then we've got some information. So new function is going to follow this rule as well. It's going to be mx plus c. And so we've got some information. That means that fx is going to be 13, minus 13 rather, x plus c. And there's too much unknown here, isn't there? So what we're going to need to do is we're going to need to also take our y value and we're going to replace our x and y value, or our fx value if you like, because if we actually labeled this graph over here, we'd have fx versus x. And so we'll replace both of those values. So fx is 18. I'm getting that from our coordinate up the top up here. X is minus 2. And so we can now solve for C. I've run out of room here, sorry. So I've got 18 equals minus 26. Oops, sorry, 26 positive minus 13 times minus 2 is positive 26 plus C. Balance method, and C is minus 8. So we've finally got that. We've got a formula we can write. So the tangent at minus 2, 18 has an equation fx, it's asked in fx, so we'll answer in fx, minus 13x minus 8. And that's our final answer. Alright, and in question 7, which is our last question, we're being asked to find the normal, and it's similar to the question above. The one above we were being asked to find the tangent, which is parallel line. The normal is a perpendicular line, so you might remember this from last year in linear equations. So it's going to look fairly sort of similar. We've got another quadratic function here, so it's going to look something along these lines. Not a very good drawing, but let's say this is our point we're discussing here, which might be 318. I'm picking that up from here. Then what we just discovered then was the tangent, like this. What we're looking for this time is the line that's perpendicular to that, and this one's the one that we call the normal. Okay, so this one was the tangent. We need the perpendicular line to that. So a very similar process. Let's kick this one off by working out what the derivative is. So this one will be, and the other thing we might just mention here as well is that we're plotting h against t here. Okay, so the letters might change a little bit as we go, but we are after the derivative, which is dh dt, just the same as x and y. Same process, just watch the letters. So we've got 15 minus 6t. So this is our derivative function. We've still got a t value here of 3. So let's sub that in. So dh dt when t is 3 will give us an answer of minus 3. And so what we might do is just make ourselves a little note over here so we don't get confused. That means that the gradient of the tangent is minus 3. So the gradient of the normal, remember we had to flip it upside down and reverse the symbol, so this becomes positive 1/3, okay? Because we're looking for the perpendicular line. So that means that if we are trying to find the equation of the normal, then what we've got is we've got the h of t, and this has to be mx plus c, okay, so mt plus c. And now we'll fill in what we know. So we know that ht is going to have a gradient of 1/3 of t, but we don't know what the c value is. And so now we need to go back through the same process. Go back to the original coordinate and substitute in the values. So we've got a value down here of 18 equaling 1/3 of 3 plus C. So we've got 18 equals 1 plus C. So balance method, and C is 17. So we've found the answer. Now we just need to write it up. So we'll go in with purple. So the normal to the curve, to the curve at point 318 is H, oh, touch screen's dying, HT equals T over 3, or if you like, a third of T plus 17. And that's our final equation.